spherical peg is attached to the edge of a horizontal disc of radius r, as shown in figure 4.1. The disc rotates at a constant angular speed of omega. So the speed is provided. And
recording in progress.
the horizontal beam is parallel. Horizontal beam of parallel light is produced with a shadow on the screen. So there's a shadow here that's moving up there. Okay. So as at time 0, the peg is at point P there, and the shadow is at S. At time t, the disk has rotated through an angle of theta. So it went that way. The peg is now at R there, but the shadow is at Q. Do you understand what's happening here? Let me explain. It's basically this, okay? So they're using the shadow to show simple harmonic motion. Oh, sorry, page is 91. So you have this screen on the background, let's say here. And a screener mothe jinishta shadow ja porbe. So the shadow of this thing will go and fall on the screen. And they're trying to trace the shadow. So what it looks like is something like this. Yeah, so you have a screen like this. Now imagine I beam light from this side, like this. If I beam light from this side, wouldn't this peg here cast a shadow, right? So where should the shadow be at this moment? What do you think? Which part of this screen would the shadow be? Amar jodi light ta hocche ekhon theke ashe. This is my light source, by the way. Okay, so the light source is on this side. So light is coming from here. As the light goes and falls onto this, right? This will form a shadow somewhere, right? Do you think the shadow will form which side? Left side. I mean, droppery. So do you think the shadow would be there, like at that location, or do you think the shadow would be at the center, or do you think the shadow would be on the side here? Yeah. At this instance, where would the shadow be? A, B, and C. What do you guys think? Yeah, so online your answers here correct, but what about you guys? Where do you think the shadow would be? Can you picture what's happening? So basically, there's a disc here that's rotating, and there's a peg here, like this wooden stick, and you're sending light from this side, right? So light is going like that. And as the light goes here, this thing will block the light and it'll cast a shadow, right? To see the shadow, you have this screen on the background. So my question is, where on the screen will this produce the shadow at that instant, at this instant? Yeah, it's obvious, but I'm very curious, what are you guys thinking about this? It's like literally in front of it, right? Shouldn't it be there, right? So yeah, the shadow is going to be at B. So yeah, it is right, the shadow would be at B. But as this thing rotates, wouldn't the peg eventually reach like somewhere there? And as the peg reaches there, wouldn't the shadow move that way, right? So that's basically what's happening. Now, surprisingly, this thing is moving in what? Circle, right? But if you look at this peg on the screen, is it moving in a circle or is it going back and forth? Back and forth, right? And when you look at the motion of that peg's movement, right, it follows what motion? Simple harmonic, because it is actually a circular motion, but which component of the circular motion are we observing? Like horizontal, right? I hope you understand. So that's the question. This is nothing to do with the answer. The question is that there's light coming out from here. This is the top view of it. So as the light goes like that, the peg at the center will block the light. So it produces a shadow there. As this thing is moving around, right, the shadow will move around as well. Okay, so that's what's provided. It says determine in terms of omega and t the angle theta. So what is this angle theta here going to be in terms of omega and t? So we have done the derivation. This is basically a derivation in their way, right? Formula for omega, 2 pi by t, but there's another one, right, which I told you is important here. Theta by t, correct? So omega equals to theta divided by t. Theta divided by t. So ora bolche in terms of omega the angle theta. So therefore theta is equal to omega t. Okay, so that's the expression. In terms of omega t and r, the distance SQ. Interesting. How can you find this distance SQ here? So do you agree that this distance SQ here is the same distance there, right? So how can I find that? Given that this is how much? r, and this is what? Omega t. So how do you find this opposite length here? Yes, very good. You take the sine function, right? So sine function curve. So if I want to do that, what should I do? Sine theta is equal to, yes, right? Sine theta is equal to, opposite is how much? The one we are trying to find out, SQ, divided by what is my hypotenuse? R. Now, what is theta, by the way? We just found omega t. So therefore, sine omega t equals to SQ divided by R. So what should the expression be for SQ? R sine omega, right? So SQ is equal to R sine omega t. Right, so these are two expressions that we found so far. Next question. It says, use your answer in A2 to show that the shadow on the screen performs simple harmonic motion. Use your answer in A2. So using this answer, can you tell me how can we prove that the object is undergoing simple harmonic motion? So quick reminder, do you guys remember what were the equations of simple harmonic motion? Almost omega square. Okay, so A equals to minus omega square x naught. That is the formula. So if I can somehow show this, then I will have my answer, right? Now, what you see here is just the equation for what? Displacement, right? So how do you convert this to acceleration? You differentiate it twice, right? So therefore, acceleration is going to be how much here? Minus omega square r cos, sorry, sine omega t. And what is r sine omega t? Displacement, right? So therefore, a equals to minus omega square r. And then what you write is that in this motion, acceleration is what? Directly proportional to displacement. And one more thing, what is it? Acceleration is directly proportional to displacement, r key. The acceleration acts in what direction? Yeah, and the acceleration acts in opposite direction. So these are the requirements for simple harmonic motion. হ্যাঁ, এখানে একটা ছোট ইস্যু আছে, এটা হচ্ছে x হবে, where x is displacement, r হবে না. So whenever they ask you about whether something is obeying simple harmonic motion or not, right, you have to somehow get to this part and that equation. Okay, so that's the theme usually. Okay, then says that the disk has a radius of 12, rotating at an angular speed of 4.7. For the shadow, find the frequency of oscillation. I really hope you'll be able to answer this. So can you tell me what should I do here? How do I find the frequency of my oscillation here? It is very easy, okay? What do you do? How do you find the acceleration here? Sorry, frequency. Yes, what do we do? Yes, very good. So we know omega is this, right? And what's the formula for omega? 2 pi by t or 2 pi f, right? So just basically that omega equals to 2 pi f. Omega is 4.7 equals to 2 pi f. So f equals to 4.7 divided by 2 pi. How much is it? 0.075. There's a question here. How can you explain the acceleration in opposites again? Yeah. So whenever you have oscillations in simple harmonic motion, right, you'll find that I'll do with the pendulum, right? So the pendulum is on the side here, and this is the center, and the pendulum is now displaced to this side. Let's say we take this side as negative. You'll find that the restoring force, the force that is bringing it back in, is actually the other way, which is positive. So you always have your displacement and the acceleration act in opposite direction. It is impossible that your displacement and acceleration will act in the same direction in this scenario, because if you push it to the left, it will try to go to the right and vice versa. Okay, so that's why it's not possible. So yeah, how do we know this? So the equation shows us, but then again, practically also, whenever you displace to the left, it goes to the right. So you'll find that the acceleration is always acting towards this line here. This is the equilibrium. So another way of writing the answer is that the acceleration always acts towards the equilibrium. But when we release it, then it's moving towards the center. Towards the center. So as it moves this way, isn't the displacement still that way? So think of it here. It's still moving that way, and the displacement is still negative. So until it reaches this line, right, the displacement and acceleration is always opposite. Once it crosses this line, it's still the same. Your displacement is going to be positive now, and your acceleration is going to be negative. So in a simple harmonic motion, the two directions are always opposite to each other. It's like a mandatory requirement. And the math checks out, right? When we do our equation, you'll find that it's negative at the end. So 0.75. Maximum speed. How do you find maximum speed? Yeah. So V max is equal to omega x naught. X naught being what? Maximum displacement. So we just found the omega, or we actually given the omega 4.7 into what is maximum displacement, which is radius 12, right? And you have to divide this by 100, no, because they want it in centimeter, right? So how much is it? 56.4. I think everything is given to two significant figures, so 56. Right. So what you have just solved is like a standard, okay, stable question from this chapter. They want you to show that there is simple harmonic motion. They want you to use the equations and find some unknown quantities. That's more or less it. Okay. So yeah, that's what we have done so far. I will give you a question today, the most difficult question possible, just to show you the two, ends of it. But Tarakde, we want to wrap up something else. So for that, can you go to page 79? Page 79. So we need to know the energy interactions of simple harmonic motion. So before I start, I need some reminders from you guys. X equals to, right, so this is the equation for displacement, okay? X equals to x naught cos omega t. Can you tell me what would the equation for velocity be then? Equation for velocity. So you differentiate this, right? So that will be omega x naught sine omega t, but with a what at the start? A minus, right? And then acceleration is going to be what? Minus omega square x naught cos omega t. And this cos omega t here, right, that part is what? X. So therefore you get what? A equals to minus omega square x. And this equation happens to be the requirement for what motion? Simple harmonic motion. So anything that obeys this is undergoing what motion? Simple harmonic motion, right? And we just summarize the whole chapter. This is exactly what we've done so far. So these three equations and A equals to minus omega square x. So what's next? So next হচ্ছে 17.2, right? Describe the interchange between K and potential energy during simple harmonic motion and derive this equation. So I'll derive it for you, but there's this equation out there, okay? So so we need to look into simple harmonic motion from the energy point of view. How does energy interaction take place? So before I start, I just want to show you this here. Understand displacement and everything. Like we are done with the first part, so I just want to do a checklist here. So understand terms displacement, amplitude, period, frequency, angular frequency, phase difference. All right. Do you remember phase difference from AS? The angle variations in like the motion of an object in terms of angle, phase. So if something is completely in phase, can you remind me what was the phase difference? Completely in phase. 180. 2 pi, yeah. 2 pi, 4 pi, 6 pi, all even numbers of pi. And when is it completely out of phase? Yeah, pi, 3 pi, 5 pi, all odd numbers of phase, right? So we still have that. That's a R to path difference, which is like lambda, and the other one is half multiples of lambda. We don't have path difference in this topic. Okay, this topic only has phase difference. Okay, because you don't have really movement to a location here. Understand simple harmonic motion occurs when acceleration is proportional to displacement from a fixed point and in the opposite direction. I would recommend that acceleration is what proportional will be better directly, okay? Because there's no coefficient or no other function. It's just straightforward, directly proportional passing to the origin. Use the equation A equals to minus omega square x and use the solution to this equation, AJ. So if you keep solving this equation, eventually you get to that. That's what they're looking for. Use this for velocity, right? And this is the other equation I told you. When to use this equation, by the way? What was the requirement for using this equation? Yeah, it's when you don't know time, you know location. So you have an oscillation and you don't know what the time of the oscillation is, but you know where the object is. So you want to find the speed at that location, okay? Interpret graphical representation of velocity, displacement, acceleration. So that's this thing, graphical interpretation. So yeah, we are done with the core simple harmonic part. Aske will deal with the energy part. Energy part is not that complicated. It's just two graphs we need to do. Right, so let's set our premise here. So this is how does energy interact with simple harmonic motion? So energy variations. It's actually quite straightforward. All you need to do is just help me plot a graph here based on values, okay? So you have this object here trying to oscillate. I want to plot a graph for energy versus time for this object, energy versus time. And you'll find there's this interesting graph that actually shows up here. So time, seconds. Right, so you have to be careful here. I use what in my y-axis? Energy. There's a problem with that reference. What's the problem? When an object is oscillating, right, what does the energy of the object do as it oscillates in a system that's perfectly elastic? In a system যেখানে কোনো হচ্ছে energy loss হচ্ছে না, how does the graph for energy look like? Yes. So if I have a pendulum oscillating in space with no energy loss out there, and I give it 200 joules, right? Perpetually, it's going to have what energy in total? 200. Because there's no energy loss out there. However, this has two parts of energy in it. One is GP and the other is what? K. Those keep interchanging. And that's what we need to see, because there's the interchange between K and E, right? So if you had total energy graph here, it'll be straightforward. What should it be? Just a flat straight line like that, right? But that's not what we want right now. We want to understand how does GP and K change, okay? So now you tell me, I'm gonna point set for kichu. We'll start with this one. This is the maximum displacement that I have, okay? And this is the center. This is equilibrium. Can you tell me at this location that I have here, right? What is my GP and what is my K? So you just need to tell me maximum or minimum or zero. Which GP is maximum? Yes. So this is GP maximum because you have taken it to a height, right? So GP max. But what about K at that point? Yeah, because you have held this in your hand, right? So therefore, there is no K here yet. So GP is maximum, and K is actually zero. No minimum, nothing is K is zero because this is at rest. So if I want to plot a graph here, my GP is going to be maximum. So let's call this the maximum value. And my K is how much at the start? Zero. So we know that the K starts from zero. As this thing oscillates, right? Next point, the object is now here. Like it's vertical right now. Can you tell me what should my GP and K be? If it's vertically like that, right? What is my GP? Zero. Achha, now, it is not true that the GP is actually zero. And the reason behind that is, isn't it still above the ground? Yeah, so we'll find the change in GP, but let's assume that the ground is the zero. Then isn't the GP zero? Like in all the GP you provided is gone, right? Of course, it can fall further. So we'll take this GP as what? Zero, okay? I'll explain in a minute. Can it is zero hour. And what about my K? Maximum, right? So whenever the object oscillates and comes to the center, it has lost all the GP. So you can see it here very clearly. It has lost all the GP and now it's just K. And then that K would become what eventually? As it goes up. Yeah, so as the object goes the other way, right? It oscillate করে এই side চলে আসলো. Can you tell me if it comes to this side, right? What is your GP and K going to be? Yeah, GP is going to be maximum and K is going to be what here? Zero, right? So that's what's happening here. So yes, now how can I plot a graph for this? So let's start to see this. So we'll give them names. This is T equals to zero. Can you tell me when the object is here in reference to my entire oscillation, how much time has been elapsed? When our total time to T hoy, when it comes to the midpoint, right? How much time has been covered? Yes, very good. T by 4. Okay, so this is T equals to T by 4. Then in this location, T by 2, right? T equals to T by 2. On its way back, it will again cross this, right? তখন time কি হবে? 3T by 4. Okay, so we'll plot for these points. So we have T equals to 0. Now this is going to be T equals to T by 4. So let's plot these values. This is T equals to T by 4. And T equals to T by 2. You'll find the graph looks a little interesting, like different than what most of students anticipate. 3T by 4. And that is T, the total time period, right? So let's try to look at the values here. GP is maximum at the start and K is 0. And K is what at the start? 0. So let's start. So, it goes from here. When you go to T by 4, what is my GP? 0. Yeah, and what's my K? Maximum, right? So that goes there. And this one will go there, maximum value. Do you understand the GP and K would be same value? Because all the GP became K, right? Acha, airport ki hobe. What happens next? Next, again, at T by 2, that location there, right? What is my K? 0, right? So K becomes 0. And what would my GP become? Maximum. So the GP is maximum again. And then again, on its way back, right? What would my GP become? 0. And what would my K become? Maximum, right? So yeah, it's a constant energy flow system. You're correct. And finally, we have here where my GP is going to be maximum and K is going to be what? 0. So once you have a system like this, right, you will find that the total energy throughout the process remains what? Constant. Okay, so that black line I've drawn there represents what energy? Total energy. But how does the GP and K vary? So what do you think? So do you think the GP is here, the GP is there, right? What kind of a graph would this look like? Like that, or like a cosine that goes in the negative axis. Right. So the thing is, there can't be any watt axis value in this graph, negative, because we're dealing with what? Energy, right? So it will be like a cosine graph, but it's a cosine squared graph. So if you square a cosine, right? Have you done cosine squares? How does it look like? like what? You're very confident. So what happens is when you square cosine graph, right? Everything that's negative becomes positive as well. Okay, because it's a cosine square. So eventually, I'll tell you what the graph looks like. You're right; it is like a cosine graph, but it is not fully a cosine graph. It is a little skewed. So এটা এরকম দেখতে হয়. Yeah, some students think that it's a modulus. Do you know what a modulus is? Yeah, this is not a modulus. That's a little different. Modulus কি হতো? Modulus the graph would look like this, right? The negative would become positive, but it's not that. This is actually the negative value getting squared, so it becomes a positive value with its own shape. So it'll look something like this. Let me draw the whole thing. So it is a Watt graph after all. Like it looks like a Watt graph, a cosine graph, right? With the entirety of it in which axis? Positive axis. So that is how the graph is supposed to look like. The reason why students struggle with this a little bit, I'll show you in a second. The reason is that, of course, you have to sketch this in your exam. They'll ask you to draw this. And secondly, they think that this is how many oscillations I'm drawing here. So at first glance, it might feel like I'm drawing how many oscillations? 2. But it's actually what oscillation? Just a single oscillation. Okay. Why is it like that? Because it actually goes back and forth like this, right? So it's going back and forth. Typically, how the graph look like? It would have gone negative and then positive, right? So all the negative part here just goes to the top. So yeah, this is how the graph looks like. Now, how the graph look like for GP? GP graph কিরকম দেখতে হবে? Sorry, K. The one I drew is GP. What's K going to be? Just the mirror opposite of it. So every time my value here is positive or it's upwards, this is going to be downwards. Why is that so? Because as the GP decreases, what increases? Ke, right? And at any given point in this oscillation, if you take the value for my GP and Ke and add them together, what would you get? At any given point, if you add the GP and Ke value, right, what would you get? Total energy. You get that black line at the top. Okay. So yeah, this is how the graph is. Yes, you are expected to draw this in the exam. Okay, sketch this, more appropriate. But do you understand that there are how many cycles involved here? 2. That's very important. Cosine graph translated outwards. Yeah, you can say that. Right, so this is the first graph. There's one more graph out there. We'll do that in a minute. But did you understand how to draw this graph? So I'll add like points based on this graph, but I hope you understood the logic behind it. So I'm basically just plotting what? The values of Ke and GP. Right, so let's label them. This one is total energy. The blue one is your GP. Okay, we need an expression for maximum K. Can you help me how to get an expression for maximum K? So let's just mass as M, right? So K maximum when it crosses the bottom here. How do I find that? So K maximum should be what? Half M V max squared. Do you agree? Do you happen to know any equation for maximum velocity? Right. So equals to half M omega x naught squared. And the plus minus doesn't matter because it's directional. So eventually what do you get here? Half M omega square x naught square. And that's what they wanted us to learn. Okay, that's the equation there. So yes, very straightforward. I prefer that students derive them so that exam, if you suddenly have a situation, you can remember them right away. Most likely they don't provide this in the data booklet. So yeah, that's the equation from maximum K. তোমাদের কি বলছিল এক্সাম আসতেছে অন alternating current, AC current, দিতে থাকবে induction, magnetism, আর কি quantum physics. Quantum physics is a very interesting chapter. একদিনে শেষ করলো, it's very unfair. But anyways, আর হচ্ছে AC supply does. Have you done the bridge rectifier? চারটা ডায়োড থেকে কারেন্ট এদিক ওদিক গিয়ে সোজা হয়ে যায়। আচ্ছা, AC কারেন্ট থাকবে। And oscillations আছে শেষ। Ideal gas এর শেষ। Ideal gas এর thermophysics করে না। টেস্ট কবে? এটা কি হচ্ছে অক্টোবর শেষে নাকি রুটিন? মানে 14th October, right? Start হবে। Done? Okay, so there's one more graph and then we can wrap up the topic. So this graph that I'm going to do right now is going to be with respect to displacement. So just somewhere put this heading because there are two graphs and students get confused. So heading out here, the first graph I've done here is energy versus time. So we did a time graph here. This is energy versus time. And the next graph we're going to do right now is going to be energy versus displacement. How does energy change with displacement? Okay, so the same pages. Energy Okay, so how does a graph for energy versus displacement look like? So for variations and different approach, what we'll do is we will not take a pendulum system. We will take a mass spring system. Okay, so this first example that I showed here was a pendulum system. Bear in mind, both the graphs I'm showing will have the same outcome for any kind of simple harmonic motion. It's not like the pendulum graph look like this. Any simple harmonic motion graph will look like this. The reason I do pendulum is because it's easy to recognize the energy changes. Okay. Similarly, we'll do now displacement. This is going to be mass spring system. So mass spring system. Right. So what does a mass spring system look like? So I think last class or maybe the class before, I told you that mass spring systems are difficult to model because as a mass undergoes oscillation up and down, right? Something interferes with it. What is it? GP and the weight, right? And why is that a problem? Because as you go up, GP is acting downwards. But as you go down, which way is GP acting? Still downwards. A simple harmonic motion must always do things that are opposite one way and the other way, right? So basically, if you're going down, the force should be up. If you're going up, the force should be down. So this becomes a problem. And does it hamper your motion? Not really, but the values don't match. So how can we get rid of that issue? So I think I told you what the solution was. There was a picture here. AJ, we do this. So what do we do here? We make the mass go left and right, back and forth on a what surface? Flat surface. And then students will argue that there's friction now. Shouldn't that be a problem? But turns out it's not a problem. Why? Friction always acts in what direction to your motion? Opposite direction, right? So eventually it does act like one of those restoring forces out there. Okay. So yeah, friction is not a problem. On top of that, we will just ignore friction. So, it's not going to be an issue with our diagram here. So for a mass spring system, what I'll do right now is this is the spring. I will compress my spring and the trolley or the mass is now fully compressed, right? And I'll draw a line here to give you idea of my reference. So reference is this line, okay? This is the origin. Now, as the mass is released, what will happen is the spring will extend. And, sorry. Just a second. This is origin. Okay, that's the compressed part. So yeah, my mass is in origin right now. And if I compress my spring, the spring goes this way, right? So my displacement is negative. But can you tell me in this particular position, which way is the spring applying force? If you have pushed it that way, right? Which way is the spring now applying force on you? The other direction, right? And it then becomes normal. And then it stretches out because it has energy, right? So what will happen is the spring will stretch out quite substantially, right? So something like this. And the mass will end up somewhere here. So now it's the other way than maximized. So this will continue to happen. Again, it'll come back to what position? The center, right? And then again, what will it become? Compressed. Can I consider this to be one cycle? Yeah, because I started from one point, I came back to the same point. Look at the mass here, right? So if you look at the mass here, it starts here. So it's basically going back and forth like that. So it goes forward and then comes back like that. Now, what we need to do is we need to plot a graph here with respect to what? Displacement. So this is displacement values that I'll be providing. You need to help me out here again. Can you tell me what is the EPE here. We don't have GPE anymore. We have EPE. What is that? Elastic potential energy or elastic strain energy, right? So in this particular instance, the first one, what is my EPE? Yes. So the EPE is max because your spring is completely compressed. And what is your K? 0 because it's stationary at this moment, right? And as you release it, it starts to move outwards and it loses all the EPE because it's now completely unwound, right? And now it has what EPE here? 0. So the EPE becomes 0 when it crosses the center. But what does K become here? Max, right? Because now you have converted all the EP to K. And that keeps repeating itself. So it keeps going from EPK, EPK. So again, if I go to the other end, it's going to be like that. And then again, if I come back to the center, it's going to be like this. And once again, if I get back to the origin, it's going to be like that. So we now need to plot a graph for this, but not with time, with what rather? Displacement. This graph is a little odd. And this graph, past paper যতবারই আসে, students struggle to read this, mainly because it's not a conventional looking graph. So you have energy here and time axis, not time axis, sorry, displacement axis here. The thing is, displacement can be actually a what value? Negative value. Unlike time, time can only be a what value? Positive value, right? So tell me this. I'll draw a line right now. This line. What does this line represent? No, just like before. Yes, total energy, right? So this is the total energy that we have, which will remain what throughout the process? Constant. Total energy will change. Now, let's consider this displacement to be negative. At negative maximum displacement, what is my GP or EP, sorry, maximum? What is my K? 0. So what I'll do right now is I'll plot that information. Somewhere K hoche 0 and my EP is going to be maximum. So I'll take this one here and place it there. And I'll take this one here and place it there. Do you understand what I just did here? So when my displacement is maximum negative, right, my EP is maximum and K is 0. As you cross the center, what is your EP? 0. So let's do that. EP is 0. And what is your K? Max, right? So that. And then as you go to the positive maximum displacement, what is your EP? Maximum, what is your K? 0. So if I replace that here, that's going to be this and that. What do you think the graph should look like? You want to go? Hey. Positive. So what should the shape look like? Like oh, you meant like this? আমার তো এখান থেকে এখানে যায় তারপর এখানে ব্যাক করে so it's supposed to be much more easier. It's a quadratic graph. It's exactly y cos x squared because I'll tell you why. Yeah, it's half kx squared, so the x squared becomes like that. So yeah, that's the graph for my GP, or in this particular case EP variation. Okay, and the graph for my K variation would be just the mirror of that. There you go. These are the two graphs. Okay, so that's our center is 0. So as the mass goes this way, it's negative, then comes back to 0, and then goes the other way, so that's positive. Spring system. Spring system is right. EP is no, when it stops, yeah, K0, EP is maximum. How do you count that? it's very easy to understand. Look at this. Okay, so this is a spring, this is the mass, right? This is normal length. If I pull it this way right now, and I'm holding it right now, what is my EP? The elastic potential energy in this maximum. But is it moving? No. So what is my K? 0. I let go of it. Let's say. What it'll do is it'll like move like that, and it'll lose all the EP, and all the EP will be converted to what here? K. So when it crosses the center, right? What is my EP? Because there's no extension, 0. But where did all the EP go? It got converted to Ke, right? So the maximum K is here. But then it will take the K and go forwards, right? So as it goes forwards, it's not compressing the spring. So spring is now converting the K into what energy here? EP. So it goes the other way and stops. And at that point, all the K is now converted to EP and my spring is compressed, right? And it's stopped right now. So the EP is maximum and K is what? 0. And then the spring pushes my mass back and it goes out like that. And what happens is it loses all the EP and it becomes K. So it's basically that. Let me see if isn't this half cycle? No, it's not half cycles. You know why? Because it'll go from here and then it'll go back there in the same graph. And because there's no time here, the graph will just be going back and forth in the same place. Yes, if you drew this with time, you'd have like this and this and this and that, right? But not in this scenario. So let me see if there's an animation on this. I think oscillation sideways, right? Right, so look at this. And yeah, do you see how the potential energy is changing? So when it goes all the way there, potential is maximum. And then as it comes here, potential is 0. And then what does it become again? Maximum. Potential means elastic potential energy, right? So it keeps changing from maximum to 0 to maximum. If that's the energy replacement, right, Ajay? That's the energy replacement for EPE. What would the graph for KE be? Exactly what of this? Opposite, right? So that's what we did here. This is the graph, right? So the graph I've given you is this. So as it keeps going back and forth, right? It does that. How would the graph look like for K? They didn't give me that option, but the K graph would be exactly what of that blue graph, opposite. Okay, so it just keeps going back and forth like that. Now, if you want to see the oscillation, I think there's an oscillation here. Yeah, so look at this. Look at the graph on the left-hand side. Okay, I'll put some mass here, and I'll make my damping none, and I'll bring it down. So right now, the EPE is how much? Maximum, right? Total energy is also that. See how it changes. Like I'll make it slow motion. Do you see how the blue graph? Wait, what's happening? No, I thought the energy was lost. Ekhane ekta problem আছে. Ekhane problem টা হচ্ছে the reason why it's not simple harmonic. Who's interfering with my process? Yeah, do you see there's a graph like P gravity graph there, right? That is actually not supposed to be there. So that's the one that's causing the issue. Can I make gravity 0? I think so. Yeah, so that's how the graph we want. Do you see the blue and the green graphs on the left-hand side? How they কেন মানে Oh, oh no, that's because there's no gravity, so I think the simulation broke. No, simulation actually body the spring will get compressed entirely. Oh no, এখানে spring এর মধ্যে থাকতেছে. I know it's not supposed to go beyond that point, so that's a bit of an issue. No, because তুমি যখন উপরে নিয়ে গেলা, you give energy, right? ওই এনার্জিটা নিচে চলে আসে। তুমি বেশি এনার্জি দিয়ে দাও and the spring goes too far, তাহলে deform হবে. In this case it won't. আমি mass বেশি করে দিই তাও চেঞ্জ হবে না। They will come back, don't worry. And because there's one third-party force that interferes with the motion. So if you do you know how to remove like in O levels we have this in background radiation. We have it in A2 as well. So background radiation is this radiation available in the background that you have to subtract into your math, right? think of the gravitational force here as what radiation, background radiation. So if you want to find true values of simple harmonic motion of a spring system, you need to subtract what from the system, the weight, and then do your math, and then that works out. Okay. No. So yeah, these are the graphs of motion, energy graphs. So our next class will start a new topic under this topic is called resonance and damping. And with that, we'll be done with simple harmonic motion. The test we had Wednesday.
Record.